Okay. Number one. Okay, a tank has height of 10 feet. The area of the horizontal cross-section of the tank at height h feet is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values for a of h are given in the table above. Part A, use left Riemann sum with 3 subintervals indicated by the data in the table to approximate the volume of the tank. So it feels a little bit strange to do Riemann sum for volume because we usually associate left, right Riemann sum with area, right? But the reason why we're able to do volume here is because A of h is not defined as feet. A of h is square feet. So normally if it was width times height, that would be area, right? But here, this is width times square feet. So feet times square feet, that's going to give us volume because we're already starting off with the second row as a two-dimensional figure or two-dimensional calculation. So that's why we're able to achieve volume because one of the rows is already area. Okay, so part A. We're trying to approximate the volume. And A of h is in terms of square feet. DH is in terms of feet. So when you multiply square feet and feet together, you're able to achieve cubic feet, which is a volume measure, unit of measure. So square feet times feet is cubic feet. Okay, so left Riemann sums, approximation, squiggly line. 3 subintervals, subtract each of the widths. 2 minus 0, 5 minus 2, 10 minus 5. Your width is going to come from those values that you found, and then your height is going to come from this row. Okay, we're not going to use a 0, 10, 5, 0, 2, 5, 10 because we've already adjusted the width there. Okay, so now left Riemann sum. Width times height. Right, so for each subinterval, we want to choose the left height. So width times height, and then width times height. Okay, cubic feet, so unit of measure for volume, 176.3 cubic feet. Okay, numbers 1 and 2 are always going to be calculator on your AP exam. Okay, part B, does the approximation in part A overestimate or underestimate the volume of the tank? So look at what's given, what's told to us though, that the function is decreasing. So if you have a function that's decreasing, then any graph that you create with a left Riemann sum is going to be an over approximation. So if you look at a graph, right, that's decreasing, and you attach the upper left corner to your curve, and you force these left-handed rectangles to show up, notice that all these rectangles are sitting with portions that stick above the curve. So we can safely say that the area under the curve is going to be smaller than the area of these rectangles. So therefore, our rectangles are going to overestimate the actual area of this curved shaded region. Okay. Part C, the area in square feet is modeled by function f, which is given by f of h. Based on this model, find the volume of the tank. So we're already sitting in terms of area. So if I do area times dh, that will give me a volume. So I can achieve volume simply by taking the integral of my area. So all this is just calculator work, right? F of h is in terms of square feet. If we do f of h dh, that's going to add another dimension of feet. So square feet times feet will be cubic feet, and this will result in the volume calculation. So you practice entering this into your calculator. Integral from 0 to 10 of 50.3 over e to the 0.2 h plus h, 101.325 cubic feet. Okay, questions so far, A through C? Part D. Part D says water is pumped into a tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 feet per foot per minute. Using the model from part C, so we have an area model from part C, find the rate at which the volume of water is changing. So we're looking for something that's involving change in volume. Now, we have to kind of understand that because you see time involved here, this is going to be a little bit of related rates. Okay, so we have to kind of prepare ourselves for that. When we know with related rates, every variable is going to get impacted by time. So we're going to be expecting a dv dt, a dh dt, okay, as we recognize the need for related rates. Now, before we can find the rate at which the volume is changing, we first have to build our volume equation. Okay, so our volume equation, we have area, so we have to involve the integral of area to reach our volume status. So the integral of f of h okay, we know we're starting at 0. Okay, this is kind of like what the tank is doing, right? It's starting at 0 feet and it's increasing, but we know that it's going to be an ever-changing, right? Water is being pumped into the tank. The height is going to continually change, so you want to allow for that upper bound to be a variable. Thank you. Got handouts there. So, but let me adjust this a little further here because we do want these to be slightly different in terms of the variable. So I'll leave that as h, but I'll just here show f of x dx, okay? Just because when we're dealing with integrals here, we typically want these to be different variables. So if I know my variable is h here, I'll usually use this as x. Okay, let's gather some information here. Okay, it says the height is 5 feet, increasing at a rate of 0.26 feet per minute. So we know our dh dt is 0.26. And it says find the rate at which the volume of water is changing. So we're looking for dv dt. So this is the information I've gathered. Height is 5 feet. DHDT is 0.26. And I'm looking for the rate of volume, dVdt. So I want all this information, but I'm starting at this V equation. So I need to be able to get to my derivative so I can have these variables to plug in and work with. So let's think about related rates. We know V becomes dVdt. And then the rest, we have to involve derivative, right? We know the derivative of an integral will just take that integral notation out. But then the upper bound is going to get inserted into the function. So this is second theorem here. Multiplied by what, though? F of h times. Good. How do I represent h prime, though? Remember, time is involved here. So times what? dh dt. Yeah. So that's the hard part. The hard part is building the equation and then knowing how to get to the derivative, because usually, right, we usually don't see a related rates problem with this integral notation, but this is what we're asked to build. Okay, so now it becomes a lot more manageable. We can replace h with 5, replace dh dt with 0.26. Right, but we're still trying to get it down to a numeric value. How can I find f of 5? Do I have something available to help me find f of 5? Yeah, calculator into the f of h, right? So no derivative here. We can just insert directly into the function, get that numeric value. .694. Unit of measure, volume is cubic feet. Time is minutes, so cubic feet per minute. Yeah, just be prepared. You know, on the AP exam, part D is usually a little bit more challenging, a little bit where it's going to kind of stretch you a little bit. So, you know, don't be stressed out if you feel like, oh, I can't get part D of some of these FRQs. You want to just you want to try your best to do the A through C or the A through B. And you know that part D is always going to be a little more challenging, okay? If you can earn a point or two, that's great. That's already very good, right? So any points that you can earn, if the last section is good, you don't have to feel like you got to do everything perfect in order to earn a 5. Remember, a 60% is good enough for a 5 on the AP exam. So even if you get half of the problems correct on each FRQ, that you're on track for a 4 because that's 50%. But the hope is that, you know, I've really been kind of stressing FRQs because I feel like FRQs are just more intimidating than multiple choice because you're staring at a blank page and you're trying to create, you know, you don't have the safety net of the answer choices like you have in multiple choice. But I'm hoping that, you know, the fact that we've seen between our classwork and homework, you know, close to 30 FRQs from these past 5 years, that things will become familiar, and then you just feel like, you know, you're seeing these problems before. The hope is for that you've seen these problems before and you know how to work through it. But at the same time, we are kind of prepping for multiple choice because these topics will show up on multiple choice as well. So, you know, all these topics that we're going over, mean value theorem, role, second theorem, first theorem, derivative rules, use substitution, right? So you know, we're still preparing, we're still practicing our multiple choice knowledge as we go through our FRQs. Okay, any questions here? Number 1. All right, let's look at number 2. Okay, number 2, this is a rate in, rate out problem. So problems. You know, we've seen these types of word problems, right? They all kind of have a similar feel to them. The escalator problem, where people are entering, you know, lining up and leaving, you know, keeping track of all those moving parts. People entering into the amusement park, leaving the amusement park, right? All those, we're going to see a similar feel with these problems. Okay, number 2. When a certain grocery store opens, it has 50 pounds of bananas on display table. Customers remove bananas from a display table at a rate modeled by f of t. So f of t is the rate at which bananas are being removed. This is a rate, not the number of pounds at any given time. After the store has been open for 3 hours, keep that in mind there. And after enough bananas have been removed from the display table, store employees begin adding bananas to this display table, and then we start seeing this G of t show up. Right? G of t is measured in pounds per hour, and t is the number of hours after the store is open. Okay, so part A, how many pounds of bananas are removed from the display table during the first 2 hours the store is open? So we know that we're talking about bananas being removed. So this G of t is not going to help us. Only use f of t because that's what we're going to be using to find, to involve the number of bananas removed. But also, we don't care about how many bananas there is to begin with. Okay, so that is not going to factor at all. It's just going to be dealing with f of t. But f of t is pounds per hour, but we want number of pounds. So can I just plug 2 into f of t? What should I do? I need to involve the what? Well, derivative will take us from pounds per hour to pounds per hour squared. Right. So what's the other direction we can take? Integral, right? So integral will allow the pounds per hour to become just pounds, right? So it'll take a rate and move it up to just that numerator unit. Okay, so we'll take the integral. So I want to accumulate the rate that bananas are being removed over the course of the 2 hours. So if I accumulate all that rate, it'll give me the total number of bananas that's been removed in that time period. So we can make the calculator do this for us. Take the integral of f of t. I have y1 storing my f of t function. Math 9, definite integral from 0 to 2. y1 is holding my f of t. So 20 pounds of bananas are removed in that 2 hour period. Okay. Part B, find f prime of 7. So f is already a derivative. F prime of 7 would be the derivative of a derivative. So we can make the calculator do this for us as well. We have that math 8 feature, that n-deriv feature on your calculator. So if you do math 8, yes. Well, it's not number of bananas, it's pounds, right? So pounds, you can have decimals, right? So I think, yeah. And typically what I would say is leave your answer in decimal form, round to 3 decimal places. They can't take off points for that and ask you for, and take off points if they want a integer value unless they specify it. Okay, if they specify round to the nearest whole number, then they'll be looking for that. But if they don't specify it, they can't take off points if you provide decimals. Okay, all right, for part B, f prime of 7, deriv and deriv. I have y1 holding my f of t. I want to know f prime of 7. negative 8.11. Okay. So I could say negative 1.119 or negative 1.120. Really, it's up to you. You can either decide to round that third value, or you can just truncate and just write down whatever. So you have some flexibility in terms of how you round. Just go to 3 decimal places. What's the unit of measure, though, for f prime of 7? Good, right? Because f of t is pounds per hour. So if I take the derivative of that, it's pounds per hour, or pounds per hour squared. Now, it says explain the meaning in the context of this problem. Okay, so we want to be able to explain the meaning without using acceleration. Okay, so acceleration is for particle motion. It's not something that it doesn't apply to this problem. And also, we don't want to say rate of a rate. It's not specific enough. So what could we say to satisfy what they're looking for and be able to earn this point here? Okay, good. The rate that the pounds of banana are removed is what? What's that keyword? It's decreasing, right? So if you say rate is decreasing or rate is increasing, that shows that's what they're looking for. That's that sweet spot they're looking for to earn that point. Okay. That's how you can reference a second derivative or explain that you understand what's happening with that second derivative. You're talking about the rate is giving you that first derivative knowledge, and then is decreasing is that second derivative there. So the rate is decreasing so that's what they're looking for to earn that knowledge and earn that point. Okay, any questions for A and B? Okay, part C is the number of pounds of banana on display increasing or decreasing at time t equals 5. So the number of pounds of bananas increasing or decreasing. We know it's going to be a rate, okay? But I find it to be easier. Well, we know it's going to be a derivative, but I find it easier if we can build an equation that will tell us the number of pounds of bananas and then just take the derivative of that. So even though this may feel like we're getting to part D, which is how many pounds of bananas there are, I find it easier to build the equation and then find the derivative. So this equation shows up again and again on these rate in, rate out problems. And it's this formula here, that total amount that we're looking for is going to be some starting amount plus whatever amount has been added minus how much is removed. So we can also apply it to this problem, right? The total number of pounds of bananas on the display table is equal to how many you started with, how much has been added, and then subtracting by how much has been removed. So I'll let A of t represent the amount, the number of bananas on the display table. Initial is how much to begin with. We know A of 0, that's 50, right? We know there's 50 pounds of bananas on display at the beginning, plus the amount added. So that's the integral of g of t, right? We know g of t is the rate minus the amount removed. That's minus the integral of f of x. Okay, I'm leaving that flexibility of t with the upper bound, but I have something that's not quite right. Can you spot something with the bounds? good. So as soon as customers enter the grocery store, this will start getting activated, right? Because customers will begin taking bananas off the display table. But are employees going to start adding bananas to the display table as soon as the store opens? Okay. Not yet, right? They're not going to do that until 3 hours after the store has been opened. So this amount added is not going to take effect until 3 hours in. Okay, we still want to leave that T upper bound flexible so that we can find out the amount at any given time later on. But that 3 needs to be in place there. Okay, so now we have the equation. Let's build the derivative because part C is asking for is the number of pounds on banana increasing or decreasing? So basically asking about A prime, right? What's A prime? So derivative, we know A becomes A prime. A of 0 is just going to be 0, right? This is a number. That 50 is going to go to 0. Okay. Third term, derivative of an integral. We know derivative and integral will cancel each other out. I can insert that upper bound in, so I get g of t. Derivative of an integral, I can insert the upper bound in, f of t. So now I want to figure out what is the rate that bananas are being removed or added at 5 hours in. So I can just insert 5 in for t and make the calculator find these values, right? So g of 5 minus f of 5. We'll see which one is larger, right? If this gives me a positive value, that means at 5 hours, there's more bananas being added to the display table than being removed. But if I get a negative value, that means f of 5 is greater, which means that there's more removed that's being added. We know that the amount of bananas is going to be decreasing at that point in time. Okay, so g of 5 minus f of 5, we make the calculator find those values for us. Simply enter 5 in for g of x and for f of x. Subtract those values, and we get negative 2.263 pounds per hour. So what that tells us is that the number of bananas is decreasing by this rate 5 hours in. It's not the rate that's decreasing, it's the number of pounds of bananas that's decreasing, right? We're just at the first derivative level. Okay, part D should feel easy because we have everything from part C to build off of. We have this total amount formula. So all we need is to figure out what is the total amount of bananas on the stand 8 hours in, right? So part D says how many pounds of bananas are on display at time t equals 8. So just insert 8 for all the t's and make the calculator do the work for us. Okay, so we take the integral from 3 to 8 of g of t. We get 58.964. A of 0 is 50. That's how much is on the display table to begin with. And then we subtract out those that's been removed, right? So f of t is a rate. We take the integral of that. This will tell us how many pounds has been removed. So after everything is said and done, 8 hours in, there's going to be 23 pounds of bananas on the display table. Okay, number 3. Okay, the function f is a differentiable function on the closed interval from -6 to 5. It satisfies the order pair -2, 7. The graph of f prime, which is the derivative of f, consists of a semicircle and 3 line segments. So I have 3 line segments and a semicircle shown in the figure above. Find the values of f of -6 and f of 5. So a lot of times we like to go through this formula. Okay, this formula of final position equals initial plus displacement, because we have a starting point, and then also we have a derivative which we can accumulate to get to our displacement. So we're going to be using this again and again here. So f of b equals f of a plus displacement for a to b of f prime. Okay. So if I want to find out where I'm going to end up, I need to know where I began and then how much progress I made in that time interval. Okay. The progress added to my starting point will give me my final position. Okay, so I want to stress this again. I know I talked about this yesterday, but it's easy to make this mistake, so I want to point this out. When you set up your particle motion formula and you start inserting values in, it's important that you match these numbers. Okay, your f of a needs to match with this lower bound. Okay, it seems obvious, but when you're working backwards, the tendency is you want to do something that will flip the bounds, right? So don't worry about the fact that you're going backwards to begin with. Just make sure that these numbers are matched. Okay, if you need to change if you want to change the bounds later, you can, but you don't want to do it without realizing that you're making a potential mistake. Okay, so match those bounds to begin with. Okay, so let me show you what I mean by that. So part A says find the value of f of -6. Okay, so that's what I'm looking for. I'm going to start off with f of -6. F of A is my starting point. So starting point is just whatever they give you. So f of -2 is 7. That's the starting point. So this is what a lot of students do. I think a lot of students realize, okay, I need to bridge the gap. So I need to go from, -6 to -2. And typically, we're looking at this saying, okay, I want to go from -6 to -2, so why not go from a smaller to a larger value? But when you do that, you are kind of messing with this formula here. So when you do that, you're messing with the formula and you're missing out on the fact that there needs to be a change in sign here. So what I like to do is just blindly go through the process of matching this value up. I'm starting at -2, and my destination is -6. Right. The fact that it's backwards is okay because we can always flip the bounds, right? Now I'm looking at this saying, okay, f of -2 is 7. That's fine. The integral from -2 to -6, I know I have to involve the integral here, but I would rather not read this backwards. So now I'm going to actively flip the bounds. But as I flip the bounds, I also remember that I'm going to change the sign. So if we flip the bounds too soon without going through this extra step, you're going to potentially miss out on the fact that this needs to be a minus sign if you want to go from -6 to -2. Does that make sense? Okay, and that's going to throw your answer off. Okay, so now that we have everything set, f of -2 is 7 minus, okay, and the integral from -6 to -2, that's just going to be a triangle. One half base times height. It's above the x-axis, so I don't have to make any sign change. Two times 2 is 4. So 7 minus 4 equals 3. We also need to find f of 5, so let's also go through the same process to find f of 5. Our starting point is f of negative 2. Okay. We're starting at negative 2 and we're ending at 5. F of negative 2 is 7. Okay, so let's accumulate the area that we see under the graph between negative 2 and 5. So negative 2 to 5, so the semicircle and the triangle. Okay, semicircle is 1/2 pi r squared. The radius of my semicircle is 2. But it's negative 2 pi because it's below the x-axis. One half base times height. So negative 2 pi plus 3. Negative is below, positive is above. So 7 represents f of negative 2. Negative 2 pi plus 3 represents the area between under the curve and between negative 2 and 5. Okay, combine like terms, 10 minus 2 pi. Okay, part B. What interval is f increasing? So remember, we're looking at the derivative graph, so we want to make our label our graph accordingly. Anything above is positive slope, anything below is negative slope, anything on the x-axis is slope 0. Okay, we make our slope sine line. Negative 6, negative 5, oh, sorry, negative 6 to 5 will be included. Those are our endpoints. Our critical points is negative 2 and 2, because these are the x-intercepts. And we just fill in, right? Anything that's above the x-axis is going to correspond with a positive slope. Anything below the x-axis is going to correspond with a negative slope. Anything above the x-axis is positive slope. So between negative 6 and negative 2, above the x-axis. Between negative 2 and 2, below the x-axis. And between 2 and 5, above the x-axis. Relative max at negative 2, relative min at 2. Increases in 2 intervals and decreases in the middle interval. So f prime of x is greater than 0. Our function is increasing on the intervals from negative 6 to negative 2, and also from 2 to 5. Okay, part C. Find the absolute minimum value on the closed interval from negative 6 to 5 and justify your answer. So absolute minimum value, that should remind us that we have to involve extreme value theorem, right? Extreme value theorem says test endpoints and test critical points. So we definitely want to figure out what is the location of the graph at negative 6 and 5. But we're asking for absolute minimum values. So do we need to test both negative 2 and 2? Since these are both critical points. Right, which one do we not need to test? Yeah, negative 2 is a relative max. Relative max has no chance being an absolute min. It just saves a bit of time. It doesn't mean that you'll get points off if you tested negative 2, but we can get away with just testing 2 because it's not asking for absolute max and absolute min, just absolute min. So we already have negative 6 and negative 5. We just have to figure out f of 2. So f of 2, insert into the same formula. f of 2 equals f of negative 2 plus the integral from negative 2 to 2. And that's going to get us 7 minus 2 pi. So we compare this with 3, with 10 minus 2 pi. Think of pi as 3, so 7 minus 2 times 3, 7 minus 6 is 1, versus 3 versus 10 minus 6, which is 4. So 1 versus 3 versus 4. 1 is going to be the smallest value. Our minimum, absolute minimum value is 7 minus 2 pi. I put at x equals 2, but I crossed it out because I don't want students to mention the 2 as an equal to that 7 minus 2 pi. The more important thing is that 7 minus 2 pi. The 2 is really is not important, right? So it's only asking for a minimum value. It's not asking for the location of that value, of that minimum value. It's only asking for that y value. Okay, part D. For each of f double prime of -5 and f double prime of 3, find the value or explain why it does not exist. So f double prime of -5, we know this is the f prime graph. So f double prime must be the slope. Okay. So the slope of my curve at at -5 is this point, which is the slope of this line segment. So I can just do rise over run and just figure out the slope at that point, which is the value of f double prime. But for f double prime of 3, that's sitting at a sharp turn. We can't find the slope at a sharp turn. So f double prime of 3 doesn't exist. Another way of saying it is the limit of f double prime, the slope coming from the left side is 2. The slope coming from the other side is -1. This is not a smooth transition between slopes. So therefore, f double prime of 3 does not exist. Okay, I'm going to work through 4 through 6 in the help session this afternoon. I'll put that up as a recording. I'll also send out a Teams link so you can join if you like. Yes. Yes, yeah. If you say that f double prime of 3 does not exist because the slope doesn't exist and not differentiable, that'll be acceptable. Okay, so your homework is the 2017 FRQs. So page 21 to 26. I'll send out a reminder this afternoon. Okay, tomorrow we'll work on 2016 FRQs as well as any last minute questions that you guys have. Okay.